Define addresses. If you're sitting at your computer and you're wondering, I wonder what my IP address is, wouldn't it be awesome if not only you could find out what it is with some basic commands, but also furthermore, understand how it works? To understand the mystery of the mask and what's going on behind the scenes with your IP address and how it relates to the rest of the network. In this nugget, it's just for you. You and I, we're going to walk through step by step the purpose of IP addresses, and then we're going to take the hood off and take a look at the details of exactly how IP addresses work so you can master the concept of IP addressing. I'm super excited, so let's jump in. Our objectives in this nugget are really simple. We want to demystify IP addresses. To understand, first of all, what they do, those pesky little IP addresses, what's their purpose in life. So we'll identify that, and then we'll peel back the onion. We'll look under the hood, and we'll check out the engine to see how exactly an IP address does its job. And we're going to get down pretty deep in the details of it. So make sure you have a sandwich or some food and are comfortable, because I'm going to ask you to participate with me as we open up and peel apart this IP address to really understand what it does, how it works, and how to master it. We'll also take a look at something that's going to come up quite frequently in the networks we deal with, and that is taking a network that's given to us and creating baby networks. What do you mean, Keith? Baby networks. Well, subnetworks. Sort of like taking a 10th Street. Let's say that somebody came up and said, hey, you've got 10th Street, and we need to subdivide it and make 14 different streets out of it. How do you do it? Well, we could take the major street and carve it up into 10th Avenue and 10th Place and 10th Court. We could just chop it up. And that's what subnetting is all about. It's simply taking a street, a logical name for a network, and carving it up into multiple smaller streets. That's all there is to it. And then we'll finalize this nugget by taking a look at some odds and ends. Broadcast addresses versus unicast. We'll also take a look at multicast, automatic private IP address assignment, and some characteristics of the MAC address as well. I'm super excited to jump in, so let's go. So what exactly is an IP address used for? It's used to give our networks names. That's the first and primary purpose of IP addresses. Now, what do I mean by names for our networks? Well, let's take a city street. So we'll take a street right here. There's the dotted line in the middle. And let's call this street, let's go ahead and call this street maybe First Street. And if we're the city planner, we can go ahead and plan that out. And maybe we create another street here. I'll put my little dotted line there in the middle. And we'll call this one maybe we'll call it 12th Street. And how about another street while we're at it? They're pretty inexpensive here. So we'll call this one maybe 3rd Street. So we're all comfortable with that. Now, why do we use street names? Well, so you can find things. So if somebody says, oh, to get to 3rd Street, just go to 1st Street, make a left on 12th Street, and then go ahead and go up to 3rd Street, and you're right there. So we can get directions, location, and we can find our way around knowing what the streets are. Also on these streets, we're going to have houses. So there's a little house. Maybe that's going to be, the address is 10. So this would be house number 10 on 1st Street. And on 12th Street, maybe we have another house. Now this house here, it could also be 10. Why? Because this is house number 10 on 12th Street, which is different than house number 10 on 1st Street. So we have a whole bunch of houses and options. And over on 3rd Street, we've got some houses too, or buildings. And maybe this is house number 4. So house number 4 on 3rd Street. So these addresses that we're dealing with up here are nothing more than street names and house numbers. Well, in our computer networks, we have the exact same thing going on. Check this out. On our computer network here, we have each of these networks, which is a group of devices who all live on the same street. And here's a huge clue. On a router, every interface connects to a different street. And that really, what that means is that the routers are the intersections between the streets. So if we were going to draw an intersection up here, we could say this is a router. And an intersection here, this is a router. So every interface on a router is a different street or a different network. And so you can kind of just take a look at your routers and say, okay, based on router 1 right here, I've got a street up here, and based on this router, router 2, I've got a street up here. I also have a separate interface that goes over here. So these circled areas are networks, and then I've got another network over here and another wide area network here. This lightning bolt right here represents geographical wide area connectivity, meaning it's not all in the same small building or same campus area. It's going across a larger distance. So maybe this is in Las Vegas, Nevada, and maybe this is in Reno, Nevada, or somewhere even further away. So going back to our analogy, we need to give a network name to each one of these network segments. And so over here, now who gets to plan this? And the answer is the person who designs the network gets to choose what IP addresses to use. So on this network segment, for example, we could call this street the 10.1.0.0 street. And we'll take a look in just a few moments in this nugget of exactly how to decode and go behind the scenes on how to interpret that IP address. And maybe this network over here is the 10.3.0.0 network. And the network between these two routers perhaps is maybe it's 10.12.0.0. Again, the network planner gets to choose the numbers he wants to use. And for the wide area network, maybe it's 172.16. something. And this network over here is 24. something. And so there's our network numbers. Now the last piece inside of this planning, just like we had house numbers up here, we also have what are called host addresses on each of these networks. So this host maybe is .50, and maybe this laptop is .51, maybe the printer is .52, and maybe the router is .1. Again, you can control what IP addresses you want to use where and what host addresses you have. So just like on a street where we have street names and house numbers, an IP address is nothing more than a street name and a house number for a given computer device. And on an IP network, every device is going to use an IP address so it can communicate. And again, this is a logical layer 3 address assigned to every device so it can communicate across an IP network. So now we know exactly what an IP address is used for. It's used for addressing in the same way that a street name and house number are used for addressing in a physical world of houses and streets. We're going to use the similar concept with IP addressing to give each network a name. In this case, it happens to be an IP address, looks like a number, and each device on those networks also gets its unique host number, which is like a house number from our analogy. So now let's take a moment to dig in and find out more about this IP address. We know IP addresses have two major components. There's the street name and the house number or host ID. And I wanted to share with you what an IP address would look like on three totally different platforms. I first want to share with you what it might look like from the perspective of a router. So here is our routers. We have router 1 right here and router 2 right here. And let's take a look at router 1 and ask Mr. Router 1 if he would show us his IP addresses. And the way you do that, this happens to be a Cisco box that I'm bringing in. I bring in Mr. Cisco. And there's lots of different routers out there in the marketplace, but Cisco is probably one of the dominant players. And if we, on R1, this is the command line interface for a Cisco router, if we do a show IP interface and say, just give me the brief overview of them, that's the command that we'd issue. To a Cisco router, this means, okay, I know what you want me to do. I'm going to show you all of my IP addresses. I'm going to show you the short version. So here's the interface names on the left and the IP addresses that they have to the right in the IP address column. So this router has 3 IP addresses assigned to it. He's connected to 3 different streets. That's what this means. He has a connection on 10.1.0.1. That's his IP address there. Another one on 10.12.0.1. That's a different interface. And he also has a thing called a loopback interface. It's 1.1.1.1. Let's take a look at exactly where those are. I'm going to bring this over here, leave it just up here so we can still see everything. And then we get out a pen and we'll annotate this together. So on this, if this was this physical router, we would say that FA1/0, that would probably be right here. FA is just a shortcut for fast Ethernet as 1/0. And I'm just going to draw an arrow. So that's his IP address on that interface right there. Now the next interface is FA1/1. So if this is interface fast Ethernet 1/1, remember every interface is connected to a different network. That would be this address right here. So who got to put in those IP addresses? That's a good question. I did, because in this practice network, I was able to design my own IP addressing structure. Woohoo! I got to pick. I got to pick what IP addresses I wanted to use on what interfaces. And the fascinating thing about picking IP addresses is that you can really use a wide variety of IP addresses, but the rule is that if this guy is connected to, for example, street 10.12 something, I'll put XX just for a moment, then this interface on this router also has to agree on that same street name. You can't have two neighbors on the same street saying, oh, this is First Street. Oh, no, it's Second Street. It doesn't work like that. All the devices have to agree on what the street name is, and then once they all agree and have the same street name as part of their IP address, then they have to have unique host IDs. So in this case, the address that router 1 has here is different than the host address is different than what R2 has here. That's perfectly fine. That's R1 and that's R2. Okay, so there's an IP address from the perspective of a router. And let's go ahead and move the router out of the way. And let's go grab another device. Let's grab a PC. So this PC represents this guy right here. So this PC right here, we'll pretend that that's this guy. Now this PC, X marks the spot, is literally sitting on this network. So I don't know exactly what his IP address is, but you know what? We already know how to find out. And the way we're going to find out is by asking this PC, what is your IP address? And clear off the screen here and do a ipconfig and press enter. And ipconfig will tell us in measurable terms what the IP address is. So this is saying that the IP address is 10.1.0.51. That's the IP address assigned to the network interface card on that computer. That's the layer 3 address for that device. Let's do one more. Let's go ahead and build another network, or at least draw another network. And let's bring in a Linux box just to mix it up a little bit. So here's a Linux box running a flavor of Ubuntu or something similar. And let's put him out here. Now, at this branch office, they've got a network of 192.168.0.0. That's the network. And then all the devices on that network have host IDs as well. So let's, and this device right here, this Ubuntu box, is living on that network. So how do we find out what the IP address is? We talked about this in a previous nugget, just mentioned it briefly. But if you're on Linux or a Macintosh, instead of doing ipconfig, we can type in ifconfig. So ifconfig, and that's going to give us some details. Now I've got a couple of interfaces here. If I wanted to narrow it down just to this Ethernet interface right here, I could type in ifconfig, just the name of the interface, and that would only show me the details on that one interface. So if we look at the details for that single interface, it's showing us that we have an IP address of right here. Let me get my right tool out. Right here. So that's our IP address. 192.168.0.1 is the IP address of this Ubuntu box, which happens to be on a network out here. And so it's a different street name, which is completely appropriate. Every single street needs to have a different street name. Every single IP network has to have a different network name. Now, one of the challenges that comes up is, Keith, you've shown us 3 different IP addresses on 3 different platforms. That's okay. Got it. No problem. But you said that an IP address has 2 parts. 2 PARTS. And those 2 parts is the street name and the second part is the house number or the host ID. And it works just like it does on our streets. We have street names and house numbers, and IP address has those two parts too. And here's the part that I want to share with you that's really important is that we are going to divide the IP address by at some point, and everything to the left of this line will be the street, and everything to the right will be the house or the host. And that's how we actually divide an IP address. So an IP address looks like four numbers. There's a number and a period, a number and a period, a number and a period, a number. And what it really is, it's representing two portions of an address, the street name or the network name, and the actual house number on the right-hand side of this magical line. So now for the mysterious demystification process, how do we know where to draw the line? I mean, in life, you got to know where to draw the line, right? Same thing here. If I draw the line like between the 192 and the 168, or if I draw the line between the 168 and the 0, or between the 0 and the 1, I'm going to have completely different street names. So the trick with understanding where to draw the line comes into play after we understand some basics about IP addresses, and that is the fact that these numbers, these IP addresses, are written in decimal, but behind the scenes, the computers are using a different numbering system. And we don't have to, but we get to understand the difference between a decimal number and a binary number, which is a bunch of ones and zeros, and we're going to do that, my friend, right now. So let's have some fun with this, with understanding our numbering system and binary. Now, binary, when somebody says binary, I want you to think that's like a light switch. How does a light switch work? You turn it on or off. That's exactly how binary is. It's either a 1 or a 0. But before we get into binary, let's just think about how we do numbering. You and I, right now today, how we work with numbers. And let's talk about the price of something. Let's say the price of something is $3,421. That's the price. Now, do you know how much that is? Yes, Keith, I do, you say. That's $3,421. And you and I can just do that immediately. We look at that number and we know exactly what it means. But I'd like to talk with you about why it means what it means. It means 3,420 and 1 because we use a base 10 numbering system. You know why we use base 10? I'm thinking that we use base 10 because we have 10 digits. You know, we have our thumbs and our fingers, and we have 10 digits on the end of our hands total. And I think that's why we use a base 10 numbering system. A base 10 numbering system goes like this. We start with 0, meaning you don't have anything, 0. And then we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what do we do? I'm stuck. Where do we go after 9? Oh, we go 1, 0? Really? Why is that? Oh, I see. We carry the 1 over. So you go to 9, you carry the 1, then you start again. And once we get to 19, we'll carry the 1 over, and it'll be 20. And then what happens if we get to 99? What happens then? Well, then you go to 100. And then you go 101. We carried the 1 over. So every time we run out of digits, we carry the 1 to the left and start again. So that's basic counting. That's pretty straightforward. But I'd also like to talk to you about, with base 10, positions. So with 3,421, this position right here is worth 1. It's the ones position. And this position right here is the tens position. And this position right here is the hundreds position. And this is the 1,000 position. And the next one over would be the 10,000 position. Do you follow me? So when we say 3,421, that means we have 3 1,000s plus 4 100s plus 2 10s to be 20 and 1 1, which equals 3,421. I just wanted to make sure we're on the same sheet of music as we discuss this numbering system together. So because we use base 10, our numbers are 0 through 9. Our least significant position right here is worth exactly 1, and this position is 10 times that. Now, how did we get to 10 times that? because it's base 10, we start with 1, and then this position is times 10, times 10, times 10, times 10, times 10. And that's how we get the 1, 10, 100, 1,000, 10,000. Good. So if you're comfortable with that, if you're not comfortable with that, pause this, go back, and this is just behind the scenes of how we do basic numbering in the world today with at least the numbering system that we're talking about right here. So now I want to draw a little line right here, and I want to give you a what if scenario. What if, instead of having 10 digits on our fingers at the end of our hands, we only had 2? 1 finger on each arm and 2 arms. I'm thinking that instead of doing base 10, we might do base 2 because that's normal to us. So if we did base 2, I'm just saying what if our numbers wouldn't be 0 through 9, which is a total of 10. Our numbers would be 0 through 1, which is a total of 2. So if this was the case, where we want to do a numbering system that is base 2 instead of our normal base 10, the least significant position starting off would be 1. So up here, our least significant position was 1. With base 2, it would be 1 also. But as we go over, our next position over, what would that be worth? Well, Keith, up here, as we took a look at the position values, because it's base 10, you said take the first number times 10. Then take that number times 10, and that's the positions. Well, that's exactly how it would work with base 2. It says base 2, the next position over would be worth 1 times 2. It'd be worth 2. And the next position over would be worth 2 times 2, which would be 4. Again, it's base 2, so we're multiplying everything by 2. And then what would this one be worth? 1, 2, 4. What would it be? 4 times 2 is 8. And what would the next one be? I just want to make sure you're with me here, my friend. Okay, awesome. It's 8 times 2 is 16. Good. Let's do it. Let's go ahead and do this a few characters out. And then what? After 16, what would we have? Okay, 16 times 2 is 32. Excellent. And next, 32 times 2. You need to write it out. I'm perfectly okay with that. 32 times 2 is 64. Let's just do one more. 64 times 2 would be what? Excellent. 128. So in base 10 up here, it looks totally normal because we have the 1's position, and I'll do this in a different color. We have the 1's position, we have the 10's position, we have the hundreds, the thousands, the 10,000s. But if we were using binary, which is base 2, and all we had to work with was 1s and 0s, the value, this is the decimal equivalent of the value places that we had, would be 1, 2, 4, 8, 16, 32, 64, 128. Now, why would I go through that exercise with you if it wasn't important? And the answer is I wouldn't. I wouldn't bother with that discussion unless it was really important for you. So I want you right now to commit to remembering this weighting value. And to do it, it's really simple. We're just going to go out 8 places. So I want you to start, and I want you to do this right now. Don't even wait. And I want it done in pencil or pen on paper. Don't do it on your computer. I want you to handwrite it out. I want you to start on the right-hand side and do 1. And then I want you to double it and double it and double it and double it, which is times 2 times 2 times 2, and double it and double it and double it. And once you've done that, I'd like you to do it one more time. So pause me. I'll be right here when you get back. Pause me, and I want you to write it out one more time. Start from the right and just go right to left. And we're going 8 positions. There's 1, 2, 3, 4, 5, 6, 7, 8. We don't need to go any further than 8. That'll serve our needs right there. All right, fantastic. Now, what we have is a cheat sheet that we can use forever. Now, I'm a dual CCI with Cisco, and I've got some Juniper certifications and some HP certifications and some Brocade certifications and so forth. But I still refer to this cheat sheet that I just taught you to create, and we'll take a look at why it's so important. So I'm going to leave it up here. 1, 2, 4, 8, 16, 32, 64, 128. I'm just going to leave that up there for our reference. Okay, so none of that's up there for our reference. Why do we care about it? Well, the reason we care about this is because computers, IP addresses that we look at in decimal, are really being used as binary numbers inside the computer. So if we bring back one of our devices, let's bring back the PC. On this PC, our address is 10.1.0.51. I'm going to put that to the side. Let's write out that number for a moment. I want you to do this with me. Don't just watch me. Do it with me. So let's say the address is 10.1.0.51. That's the IP address that was on that PC, and I'll just label that too. So we see this number, and what they call this, they call it dotted decimal. Let's talk about that for a moment. Dotted decimal. Now, what is decimal? That's our numbering system that you and I use. Base 10, normal, everyday numbers. And the dotted simply means they put periods right here between each of the numbers. So it's 4 numbers separated by a period. Why? Why the period? Well, if we didn't have the period, we just had 101051, it might be, this and this and this instead of, so somebody might look at it and think it's one, just to keep them in order. Just like we use commas inside of decimal, we're going to use periods to separate those details so that we know it's a 10 and not a 101 as an example. Let me back those off. So that's dotted decimal. So what do we know about IP addresses? And we're talking about IPv4 at the moment, by the way. We'll get to IPv6 in a minute. So IPv4 is done in dotted decimal notation. That's a fancy word for saying that's how it's written out. And behind the scenes, the computer is actually looking at each of these numbers as a binary number. And I'm going to write down looks at it as binary. So if you're looking at this, it won't confuse anybody. So I'll say the PC, meaning the computer, looks at it as binary, meaning the 10. The whole reason we do that in dotted decimal is for humans, for us, to make it simple for us. But the computer is actually using a binary number. So let me teach you how to convert. I want to teach you how to convert a decimal number like 10 into binary. Are you ready? I think you might like this. I hope you might like it. It's an important skill either way. So let's go ahead and take a look at how to convert this. What we would do is this. We would take the number 10 in decimal, and we would say to ourselves, does 128 go into 10? So I'm going to put 10 up here. We're just working with this one number by itself. Does 128 go into 10 at least one time? Yes or no? If the answer is no, we're going to put a 0 in that placeholder because there are no 128s in 10. We'll do a couple of these. You'll get more comfortable with it as we go through. So then we take the remainder, which is still 10, and we say to ourselves, does 64 go into 10? And we're going to say, nope. So you put a big goose egg. The answer with binary is always going to be yes, a 1, or a 0, a no. So we take the remainder of 10, and 32 doesn't go in, and 16 doesn't go in, but now it's getting exciting. Okay, so now the excitement starts. Then we take the remainder of 10 and say, does 8 go into 10? Yes or no? The answer is yes. And it's only going to go in one time because if it goes in more than once, we have a problem somewhere else. So you start on the left, you work your way right, and the remainder is now how much? What's the remainder of 10 minus the 8 that we're representing by this number? It would be what? What's the leftover? You got it, 2. So then we take this position and we say, does 4 go into 2? I mean, at least once. And the answer is no, it doesn't. So what's the remainder? It's still 2. Does 2 go into 2? Yes or no? Yes, it goes in. Okay, now we have a remainder. We're going all of these 8 places, and 1 does not go into 0, at least once. So we have a 0 here. This, my friends, equals 10 in decimal. That's how you convert. What we just did, we took a decimal number and we converted it into binary. So if somebody walked up to you and they spoke base 2 only, which is binary, 0 or 1s, and they wanted to say that they were 10 years old, They would say, I am 0.0001010. That would mean 10. 10 in decimal. So let's do one more. Let's do, and what happens is each of these numbers right here, each of these numbers in decimal is representing 1 byte of data. And a byte of data, BYTE, equals 8 bits. And that's why I had you write out this conversion chart for these 8 bits, because those are the weights of the 8 bits. So this IP address 10.1.0.51, the computer sees it as 32 bits. 8 bits plus 8 bits plus 8 bits plus 8 bits plus 8. Look at that, there's 5 8s there. 8 bits plus 8 bits plus 8 bits plus 8 bits right there. So 8 and 8 is 16, plus 3 more is 24, plus 8 more is 32. 8 times 4 is 32. So the computer sees an IP address as 32 bits from left to right. We write them out as dotted decimal for convenience, but behind the scenes, the computer is working with those as if they were in binary. So when we say 10, it sees this. Let's do another one. Let's convert this number right here, a 1. You ready? So how do you convert 1 in decimal into binary? You start from the left, and you use this magic chart right here, and you say, does 128 go into 1 at least once? And the answer is no, and 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 yes. So 0.0000001 in binary equals a 1 in decimal. All right, let's do all of them. We just did 1. So we've done 10. I get my right tool here. We've done 10. We've done 1. 0. Any guesses what 0 would be in binary? It would be 8 zeros. 128 doesn't go in. It'd be 0.000000000. You got it. All zeros. That's the third number. Now, sometimes we'll refer to these as an octet. An octet is a fancy way of saying 8 bits. So we could say this IP address is 32 bits long. It's made up of 4 octets, which is 4 groups of 8. And those 4 groups of 8 are separated by periods just for convenience so that we know where one number starts and the other number stops. Let's do 51 right here. So our goal here is to convert. And I want you to practice this. And I'm going to give you a little homework assignment here too. In fact, let me give you your homework assignment right now. Make a note. I want you to take your IP address that you have on your computer. And so here's the homework assignment. I want you to take the IP address that you have on your computer. Don't wait for tomorrow, but sometime today. Take the IP address that's on your computer. You know how to find it with ipconfig. If you're on a Windows machine, or ifconfig if you're on Mac or Linux. And that will give you your IP address. And what I'd like you to do is I would like you to convert each of the numbers of your IP address. There's going to be 4 numbers. They're separated by periods, dotted decimal notation, and I'd like you to convert them into binary. We've done 3 examples so far together. We're going to do the last one, 51, right now. How do you start? You always write out the key. These are the decimal weight values for each of the positions in a binary number. So you write that out, take 51, you jot it down and say, does 128 go into 51 at least one time? No, it doesn't. Okay, cool. Does 64 go into the remainder, which is 51 still because we didn't take anything away? And it doesn't. So we take the 51 over here, and does 32 go into 51? I would recommend doing this the first few times you do it. I would just say, okay, 51, 32 does go in, so we'll put a 1 there, and then subtract 32 from 51. So we're going to borrow, and we have 9. And then we have a 1. So the remainder is 19. So you bring the remainder over and you say, does 16 go in to the remainder? Yes, it does. So this 1 right here represents a value of 16. And then you take 19 minus 16. You have 3 left. So you have 3 here. It doesn't go in. 8 doesn't go into 3. And we have 3 still left over. And we have doesn't go in. And we have 3. It does go in there. And the remainder is 1, and it does go in there. So the binary number for 51 is 00110011. So I want you to have that skill. I want you to be, at this moment, I'll just be straight up with you. This is just a parlor trick until I share with you how you're really going to use this. And you're going to use it to figure out what the heck is going on in your network. It's going to be an important skill to have. So you've got your homework assignment. Make sure you do it. Take your IP address that you have and convert the decimal number into binary. So Keith, what if we had a binary number for whatever reason and wanted to convert it into decimal? How do you do that? Well, let's take this binary number right here, which we already know what it is, but let's convert it, and let's convert it into decimal. The way you do that is you take any of the values that are on. So this would be no 128s, no 64s, 132, plus we have 116. It's always with binary, it's always going to be there's one of these values or there's none of them. And then there's going to be no 8s, no 4s. We have a 2, so you add that 2 value, and we have a 1, and then add them up. So we take 32 plus 16 plus 2 plus 1, and we'll do it longhand. 6, 7, 8, 9, 10, 11, 3, 4, 5, 51. See how that works out magically? And what I'd also like to do is have you confirm your work. When you do your homework, not only convert your numbers from decimal into binary, but also reverse it. Now, I know you already know what the answer is supposed to be, but that's a great way to double check your work as you convert from the binary over to decimal. Well, now that we've discussed together the conversion of an IP address, and we're talking about IPv4 specifically, we now have the opportunity, you and I, to take it to the next level and continue to look under the hood of IP addresses. And let's go back to our PC. So here's our PC that's on our network. And what was the command again? What was the command to verify or view the IP address on a Windows machine? Can you remind me? What was it? Fantastic. IPconfig. IPconfig. You rock. Way to go. Okay, so here's our IP address. It's 10.1.0.51. And what do we know about that IP address? Well, we know a couple things. Number one, we know that it's written in decimal for our convenience, but the computer is really looking at that as 32 bits. 32 bits of data, 32 ones and zeros. And the second thing we know is that there's a dividing line, but the question is, where is the dividing line? Is it between here or here or here? Where exactly is the dividing line? And I'd like to share with you now the dividing line and how it works. And the dividing line is something called the mask. The mask has lots of different names. Some people call it the subnet mask. Some people just call it a mask. But regardless of what we call it, the mask's job is to identify exactly where the dividing line is between the network portion on the left and the host portion on the right of the dividing line. So let's take this number of 255.0, which is this number right there, and let's convert it. Let's convert that into binary. Now, for some of you, this is going to be really simple. And for others, it's going to be a little bit of a challenge up front, and then it's going to be very, very, very simple. So to that end, let's do it together. So let me move this out of the way. And let's convert those numbers. The very first thing to do when any type of conversion you're doing is write out your conversion key. which is the weight values for the 8 positions inside of 1 byte of data. So it's base 2, binary. That means we only use zeros and ones, those 2 values. We start with 1, and then you multiply it by 2. So 2, 4, 8, 16, 32, 64, 128, and that's it. That's the 8 positions of the 8 bits inside of a single byte of data. Fabulous. So the next thing we're going to do is we're going to convert number 255, which is in decimal, and I want to find out what the binary equivalent of it is. You ready? Okay, so let's do this together. 128, does it go into 255? Yes or no? And the answer is yes, it does. What's the remainder? Now, there's a couple of ways of doing this. You could use a calculator, I suppose, or you could do it longhand. We could do 255 minus 128 and decide what that is. So what is that? So if we borrow 4, 8, I'm thinking that's going to be 7, and that's 2, and that's a 1. Let's go 127. So after we represent 128 by this 1 in that 128 position, the remainder is 127. So bring the remainder over, and then you say, does 64 go into 127? The answer is yes, it does. And then you subtract 64 more from that. What's left over? Let's do it. Well, there's a 3 there, and borrow that as 63. I've got 63 left over. Great, so you take that over here, 63. And then you say, does 32 go into it? Yes, it does. What's the remainder? 31. Does it go in? Yes, it does. You can do this longhand. You get the gist. And the remainder of that's going to be 15. Does that go in? Yes, it does. The remainder of that 7. It goes in. The remainder of that is 3. I only know this because there's a trend happening. And that trend is that it's all ones. What 255 is the highest possible decimal value you could ever have for an IP address for 1 octet, and that's because all of the bits are on. I wanted to walk you through that as a reminder of how to do the conversion from decimal to binary, and also to represent that a 255 in decimal is 8 ones, 8 bits that are on. Okay, so now that we've had a review of that and also understand that a 255, let's take a look at my IP address again. My IP address is 10.1.0.51, and the mask is 255, 255, 255.0, and I want to show you what those mean. So my address in binary is, well, we'll do decimal first, 10.1.0.51, and the mask, so that's the IP, and the mask is 255.255.255.0. All right, I'm going to get a different shade of pen out so I can leave those 2 up there. All right, so here we go. The IP address, let's do that here. IP in binary is 0000. There's no 128s, no 64s, no 32s, no 16s. There is, however, an 8, and there's a 2, and I only know this because we did it earlier. Also, if you work with these for a while, they become a little more second nature. But you know what? You don't need to feel bad about if you don't like, oh, I have those committed to memory. Just use your cheat sheet. 1, 2, 4, 8, 16, 32, 64, 128. Anytime you need it, and feel free to refer to that often and early and often. So that's the 8 position plus 2 more in that position. That's a 10. So there's our first octet. Next octet is 4 zeros, 3 zeros, and a 1. Next octet is a piece of cake. It's 8 zeros. And the last octet is 51. So we did that earlier as a review. Let's do it again. So for 51, there's no 128s. There's no 64s. There is a 32. So if we take 32, we're working on 51 here. 51 minus 32, we get a borrow there. That's a 9. And then we have a 19 left over. Okay, so we have the 32 position on, and we have 19 left over. That means there's a 1 in the 16 position, and there's 3 left over. There's a 0 in the 8 position. There's going to be a 0 in the 4 position. And then there's going to be a 1 there and a 1 there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I did my math all correct, which I hope I did. So we had a 32 on, yeah. Okay, so we should have 1, 1, 0, 0, and a 0 up there. So that's our whole binary number. Woo! What a review. What a review. I have learned also that if I walk students through this with me, not just show them, but walk them through several times, it helps reinforce the concept. So that's our IP address. And the second piece that we saw from our drawing was the mask. And the mask was 255, 255, 255, 0. In binary, that would look like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And this guy, 0, 0, 0, 0, 0, 0, 0, 0. So there's the two components of our IP address. We have the IP address itself. I'm sorry, the two elements that are shown in the config anyway. We have the IP address and we have the mask. The job of the mask is very, very simple. Brace yourselves for impact. The purpose of the mask is to tell us where the dividing line is between the street name, the network name, and the house number or the host number. And it works like this. You follow the ones in the mask until they stop. And when they stop, you draw the line. Put that 1 back there. So everything to the left is the street, which we also affectionately call the network, and everything to the right is the actual house number, also called a host ID or the host number. That's it. That's it. So why do we go to the binary? Because without really understanding how it's working, going under the hood, if you will, it's almost impossible to get. So the IP addresses that we work with today with IP version 4 are 32 bits long. We represent them in dotted decimal because we're human and it's easier to write out. Can you imagine having to configure all ones and zeros for an IP address? It would take a long time. The mask is simply a mechanism, also the computer sees that in binary, that identifies exactly how much of that 32 bits is the street, in this case everything to the left of the line, and what is left over on the right hand side is host addressing or host bits. So we could say that this computer lives on street 10.1.0, and then anything past the line, because this is the third octet, you just go ahead and leave it as a 0. You have to represent 4 octets all the time. So for the network, because there's nothing to the right of that last octet, you put it as 0. And we could say also that this host, my PC, is host 51 on the network of 10.1.0. So when we write it out, it looks like this. So it's all kind of mushed together, but it's really representing two distinct parts. A street name of 10.1.0 and a house address or host address of 51. Another way to represent this is we could count the number of bits. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're counting the bits in the mask. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24 bits in the mask. Let's do this. That's CIDR notation for representing CIDR. That's classless interdomain routing. CIDR is the acronym. And that's just another way of representing how long the mask is. So if somebody says the mask is 255.255.255.0, or they say the mask is /24, they are both representing 24 bits of network, which means the last 8 bits are representing the actual house number or host number. So let's take a look at a few other details that are really important to be aware of. And one is, what IP addresses can I use? Can I use anything I want? If my network is a closed network, meaning I'm just this, I'm not connected to anybody, Can't I choose whatever IP addresses I want? The answer is absolutely yes, you can. However, if you want to connect out to the world and reach out and connect to other devices, we probably want to follow some general rules. On the internet, and I know the real internet looks a lot bigger than that, there's the Internet Assigned Number Authority, IANA, that's responsible for managing all the IP address space out there. So for companies who just want to do private networks, they created something called, there's some standards for creating private addresses, and they're real simple. The private addresses are, and I would jot these down as well, anything that begins with 10. Anything that begins with 10, and that's going to be a /8, by the way, is going to be considered a private address, meaning you can use them as much as you want. So companies like Cisco, companies like Juniper, companies like HP and so forth, they could all use the 10 anything networks as much as they want on their private networks. They don't have to worry about overlapping with anybody because the internet doesn't let the 10 networks flow through the internet. So it's all stopped pretty much at the border of your service provider. It doesn't let it go out. Another private address range is the 172.16 through 31.x.x, and that's a /12, meaning that the first 12 bits are the network range, and with this network, the first 8 bits are. So if you see any IP addresses that are starting with 10 or start with 172.16 through 31, you know that those IP addresses are in the private address space. They're reserved. And there's one other range that you want to be aware of, and that's 192.168 anything. And that's a /16. And what these are, there's a request for comments. The RFCs are documents written by a lot of really amazing people and groups of people that talk about standards. And the standard for these private addresses, the primary one was written a long time ago, is RFC 1918. And I would remember that too. So RFC document 1918 talks about the private address spaces, and these are what they are. Now in 2012, which is when I'm recording this, they actually added another one as well, but in no way did it have time to make it onto the Network Plus certification. So just be aware that these 3 categories are considered the private address space that you're going to be seeing and dealing with quite a bit in virtually any network of any size as you work with IP addresses. Another really important and sometimes overlooked item is something called classes of addresses. Now, my mom told me that it's not nice to put people in classes. At least we shouldn't judge others. And I totally agree with that. But for IP addresses, because there's just numbers, it's not so bad. And there's 3 classes of addresses. There's class A, B, and C. Now, why do we care about class A, B, and C? It's because by default, a class A address is going to have a /8, which means the first 8 bits are the network and the last 2nd, 3rd, and 4th octets are all available for host addressing. A class B address by default is going to have a 16, and a class C address is going to have a /24. So this would be 255.0.0.0. This would be 255. What? How do we represent 8 more bits that are all on for a mask? 255, you got it. Good job. And a class C is 255.255.255.0. So just because a mask is a /8 or a 16 or a 24 doesn't mean it's a class A, B, or C addresses. There's also some ranges, and these were developed way before they knew that the internet was going to be what it is. So I'd also like you to jot down not only these 3 classes of addresses and what their default masks are for those each class of address, I'd also like you to jot down the first octet, the ranges. So how do I know if an IP address is a class A address? If the first octet is between 1 and 126, that's a class A address, which means by default it's going to have a /8 mask by default. You can change that, and we do all the time, but by default, a class A address, the first octet is between 1 through 126. So this network down here, in fact, let's take this router. Let me bring in a router. So here comes Mr. Router. He's in place. My question is, the router interface, the fast Ethernet 1/0, here's his IP address, 10.1.0.1. Is this a class A, a class B, or a class C address? Now, the only way you can tell is looking at the first octet. No matter what the mask is, because we can change the defaults, and we usually do, if you look at that first octet, the 10, that first number, because that 10 falls squarely in the range of 1 through 126, it's a class A address, and it will be forever. Well, until IPv4 is no longer around, which IPv4 is not going away anytime soon. So that's how we can tell it's a class A address. A class B address is 128 through 191. And you might say, well, what happened to 127? Anything that starts with 127 is your computer is going to think that itself. So this computer thinks 127 anything is itself. This computer thinks that 127 anything is itself. This printer, although not very smart, thinks that 127 anything is itself. The server thinks that, the router thinks that, everybody thinks that 127. So they call this a loopback range or a loopback address because really everybody believes it belongs to them. It's a long story, but that's how that works. So 128 through 191 is a class B address, and by default, the mask is going to be a /16, meaning half and half. The first half of the IP address is the network. The back half is representing the actual host ID. And then we have 192 through 223 is a class C address. And by default, a class C address is the first 3 octets is the network, and the last octet is the host address. So you might say, well, what happened above 223? Keith, I thought the max we could go for 1 octet was 255. Well, that's true. So in the 224 range and up a little bit is going to be multicast. Multicast? What do you mean? Well, hang on to your socks. In our last piece of this nugget, we'll take a look at multicast, but just know now that anything that starts with 224 all the way through 239, anything that starts that first octet with 224 all the way through 239 is a multicast address. Again, and all this is for IP version 4. So that's the under the hood portion of IPv4. We did a very thorough covering of the details of it, and we have a couple more pieces to add. But before we go on to like custom subnetting and some other cool details that it can do, I'd like to take a look at IPv6 and talk about IPv6 for a moment. We're going to use this router as an example to demonstrate quite a bit of that. Why do we have 2 versions of IP? And the answer is quite simple. Many, many years ago, when they were developing IP, the guys on the IETF, the Internet Engineering Task Force, they had no idea that it would be as popular as it is. And so over a decade ago, the same group of very smart people, which it grows every day by people who want to join the IETF, have developed the standards for something called IP version 6. And it's been out for more than a decade, but over the last several years, it's got a lot more traction and a lot more implementation. And IPv6 is a logical layer 3 addressing scheme, just like IPv4. Just like IPv4, IPv6 has 2 components. There's a network portion and a host portion. And guess what the dividing line is? The dividing line between an the host portion and the network portion is the mask. So the mechanics are the same from that perspective. And what I'd like to do is show you some details on R2 or R1, one of these routers, regarding IPv6. So I'm going to go into configuration mode on this Cisco router. You do that by typing in something called configure, and I'll type in the full thing for you. Exit takes you out. So on a Cisco router, you type in configure space terminal. And what that tells the router is, I would like to configure you from the terminal that I'm sitting at. And you press enter, and it puts us into something called configuration mode. If I wanted to go in and configure this interface right here, I could like walk into that room by saying interface fast Ethernet 1/1. So the 1/1 generally refers to slot number 1 on this modular router right here, and then port number 1. So that's what that refers to. So now my prompt changes. It says, oh, you're now in interface configuration mode. It's not telling me exactly which interface, but if I look at the line above, I can realize, okay, whatever I type here, I'm configuring for the interface called fast Ethernet 1/1. So with an IPv6 address, I'll assign one. I'm going to type in IPv6 address. And an IPv6 address, hold on to your hats, it's 128 bits long. It's not 32 bits like an IPv4 address, it's 128 bits. And so to help with that process, instead of using dotted decimal, we're going to use hexadecimal. And that deserves a moment of discussion. So let me get out a pen and let's talk about hexadecimal for a moment. So with hexadecimal, let's count in decimal first, and then we'll go to hexadecimal. So if we were counting in decimal, which we all know how to do, we would start with 0. Like for example, if you have 0 oranges and somebody doesn't give you any oranges, how many oranges do you have? 0. So we're starting there, and we'll go to 1, 2, 3, 4, 5, 6, 7, 8, 9. And because we're out of digits, we carry the 1 to this column, we put a 10, and then we start again. 11, 12, 13, 14, 15. So that's 0 through 15. How many characters is that? How many numbers? Well, it's actually 16 numbers. 0 through 16, or through 15 is 16 numbers. So if we were going to do this in binary, I'll do this over here in binary for short, just a few of them. If we were going to do binary, I'd do 0, 0, 0, 0, which is 0. And this is the 1's position. This is the 2. This is the 4. This is the 8. Let's do 4 bits for fun. And if we want to do 1, it'd be 0, 0, 0, 1, 0, 0, 1, 0 for 2, 0, 0, 1, 1 for 3, 2 plus 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Just going to check my math here. Looks good. So that's 7. And then we could go all the way. So that's 7 I just did. And we could go all the way through 15. In fact, if we went all the way to 15, it would be this. It'd be an 8 plus a 4 plus a 2 plus a 1. So I'll do the bottom row, 15. So here's decimal on the left. We have binary on the far right. And with hexadecimal, what we do is it's base 16. So if we with any numbering system, you have 0 to start with. And also with base 10 or base 2 or base 16, we simply have the first position is we start counting, you count by 1. So here we have a 1 in binary, 1 in hexadecimal, which I'm going to put right here, and a 1 in decimal. So as we continue counting, 2, 3, 4, 5, 6, 7, 8, 9, and I'm gonna move my column over here, hex. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, decimal's base 10, so once we use the 10 characters 0 through 9, we have to carry the 1. Hexadecimal is base 16. So we don't have to carry the 1 until we hit 16 characters, 0 through 15. So what we're going to do is this. This is a 9. In hexadecimal, an A is 10. And then a B is 11. And a C is 12. And a D is 13. And an E is 14. And F is 15. And guess what? If we went to 16, it would look like this. We carry the 1 and start again. So this is a 16. I'll just circle it right there. That's a 16 in hexadecimal, a 1, 0. Because we have a 1 in the 16's position, and we have a 0 in the 1's position. So that's as far as you need to go, though, with hex. Because the good news is that every character that we represent in hex is going to be either a 0 through F. So the only tricky part is anything between 10 and 15, and I would recommend you write those out. I mean, 0 through 9 we all have, but I would jot down for hexadecimal that A represents a 10, B is 11, C is 12, and so forth. Now, why? The reason for that, the reason it's important is because when we write out IPv6 addresses, we're going to be using hexadecimal, which means one of these numbers. So let me give you an example of configuring this. So for an IPv6 address, I'm going to use a question mark in a Cisco world that simply tells you what the options are that you can put in. And I'm going to put it in the IP address of 2015. Just a number, not a year. In fact, let me choose not 215. Let's use 2123. So that's just a number. That's all it is. And what that is, that's 4 hexadecimal numbers. And if the first grouping of numbers for a routable address, it has to be from 2000 to 3999 for the first number. And that's a globally routable IPv6 address that we could use on our computer networks. Let's go back to R1. All right, so see right here it has this X. That basically is telling me to put in my IP address, and I can put 4 characters at a time, and then I'm going to put a colon. So behind the scenes, what this is this is a hexadecimal character, which really represents 4 bits. And so if I have 4 of them, times 4 is going to be 16 bits. So what we're doing is we're representing 16 bits and then using a colon. You know, in decimal, we did dotted decimal to separate one decimal number from another. Here, we use colons to separate one group of 16 bits from the next group of 16 bits. And there's going to be 8 of them. So we're going to have 8 groups. I went off the edge of the world there. 8 groups of 16 bits represented in hex. So let's go ahead and add a few more. Let's say this second grouping is all zeros, and this grouping is all zeros, and that's 3. And let's put a 0, 1, 2, 3, and we'll put a hexadecimal character in, like an 11. There's an 11, and there's a 12, and there's a 13 in decimal. All right, well, 13 in decimal is an E, and a 0 again, and then we'll put some more numbers in there, and let's count. So we've got 1, 2, 3, 4, 5, 6, 7. I need one more group. Okay, now it's time for the mask. Now the good news is with IPv6, when we put a mask in, I'm just going to say /64, which means that, let me bring this over so you can read it. Which means that the first 64 bits are going to be the network, and the last 64 bits are going to be the host ID. So what this means is the computer, the router, in this case, is that this part right here, as 64 bits, that's all network, and these 64 bits are the host ID. And we'll press enter. Now, see how easy that is? But the goal is there's so many possible IP addresses with IPv6 because there's so long that we're not going to run out in the foreseeable future, not in my lifetime anyway. And with IPv4, we've already run out. So we're recycling and we're reusing, but we're effectively out of IP address space for IPv4. Now, if we wanted to, on a Cisco router, if you wanted to get out of configuration mode, we could type in end. And if we want to see that interface we just configured, we can say show IPv6 interface for fast Ethernet 1/1. So these are little shortcuts. I said I want to see all the IPv6 related information for interface fast Ethernet 1/1. And I think I can even add this command too. And show IPv6 interface. Let's just do this brief. That's going to show me all of my IPv6 interfaces, just a brief view. I want you to pay special attention to what happened right here. So I have this highlighted, and I'll bring up a pen as well. And you'll notice we put in this 64-bit IP address, this whole beautiful thing. And what it did, check it out, it only has 1, 2, 3, 4, 5, 6. We put in 8 and it only put in 6. One of the shortcuts is if there's 2 or more consecutive groups of zeros, you can go ahead and use a double colon only one time per IP address to represent that there is one or more groups of zeros that you just are too tired and too lazy to write out. You're not really too tired or too lazy, but you don't have to. And that's a shortcut. And you can't, if we had zeros here too, we couldn't have colon, colon here and colon here because the system wouldn't know, oh, are there 2 groups of zeros here and 1 group here or vice versa. So you can only use it one time, and that's what's happening right here. You also notice that the leading 0 got left off. So right here for 1, 2, 3, we don't have to put in a leading 0 in a group of 4 that we have because it says, oh, 0, 1, 2, 3, that's the same as 1, 2, 3. The leading 0 means nothing. I understand that it's simply a 0. So the double colon is a trick, and the leading 0 you can drop off. And that, my friends, is an example of an IPv6 address. And there's a whole world that we could talk about with IPv6. But for the purposes of Network Plus, I wanted to give you a little bit behind the scenes look at IPv4 and IPv6, primarily on IPv4 though, show you what the format is of an IPv6 address. It's 128 bits in length. Part of this IPv6 is the network. Part of it is the actual host. It's the actual mask that's telling us how much of it is the network and how much is host. And it's represented in hexadecimal. And that's simply because there's more numbers that, if we did it in decimal, it would be icky. It would be longer to write out and longer than it even is in hex. So by using hexadecimal, it's less typing, even though we have to understand the basics of hexadecimal. One of the other fun topics that we get to deal with on a daily basis, and I know that for Network Plus, they're not going to have you designing networks, but I want to give you an insight to how it really works, and that is to create something out of nothing. Isn't that a good trick? Create something out of nothing. Now, in a computer network, maybe corporate, maybe this is a branch office of a much bigger company. So if this is a branch office of a much bigger company, maybe they want all of our IP addresses to fit inside of a certain network space. For example, maybe they came to us and said, you know what, Keith and team, what we would like you to do is we would like you to go ahead and use this network space, 100.2.0.0/16. How many networks is that? That's one network. And maybe they said, we want you to make your entire branch, and we'll call this our branch office for right now, make your entire branch fit inside that address space. And you say, well, we have a little problem. What's that? They said. Well, Keith said in Network Plus that every interface in a router is a different network. So that means we have one network here with all these guys, and we have another network going over to router 2. Let me clean that up a little bit. So we have one network right here with all these guys. We have one network that's kind of like a private party line between the routers and headquarters. We have another interface here for our servers. We've got a wide area network connection going out to our remote network. And then we have a connection to our service provider. We're going to need more than just one network. We're going to need like 1, 2, 3, 4, 5 networks. That's, we can't, you have to give us 5 street names. And they said, no, what we want you to do is we want you to create sub networks from this one network that you've been given. So if that's our objective, if that's what we've been required to do, I want to show you exactly how that's done. And some of this, just as a heads up, you're not going to be required to create individual subnetworks in the world of Network Plus as far as certification goes, but this is going to open the door to bigger things. So as you continue on your journey inside of Cisco or Hewlett Packard or Juniper or whoever, having a good foundation of how this works and a good head start on it will serve you very, very well. So for that intent, I'm doing it. So our goal is to fit inside the space 100.1.0.0. Let's say that's our goal. So if we want to do that, we are going to use a really cool technique, and it's one you've already seen, and we're going to put the binary values again in our key. So these are the decimal weights of the binary positions: 1, 2, 4, 8, 16, 32, 64, 128. So those are our 8 positions. And I'm going to leave that permanently so they're sitting there. The next thing we'd want to do is we would want to say, okay, how many subnets do we need to create? And let's say we want to create 8 subnets, 8 new subnets. To get to 8 new subnets, the question is, how many bits? For example, we have 16 bits being used for the network right now. What we're going to do is we're going to change the mask to be 17 or 18 or 19 or 20. And we're going to take some of the bits that usually are used for host addressing, and we're going to use those to create logical subnets. It's sort of like taking 10th Street as a whole and making 10th Lane and 10th Avenue. So we have the 100.1 network to work with. We're going to subdivide it and carve it up. So the first question is, how many bits do we need to steal or to use above and beyond the 16 to create our new subnets? And there's a game that I like to play called the thumb game. And here's how it works. I'd like you to do it with me. I'd like you to look at your thumb. And on your thumb, I want you to have the number 2 written down. You're going to just trust me on this for a few moments, then you'll get it. So look at your thumb, stick it up like Fonzie, a thumb straight up in the air, all the rest of your fingers closed in a fist. Your thumb has the number 2 on it, and I want you to pretend that your thumb is a bit. If you take 1 bit and steal it from the host bit side, you can create 2 subnetworks. If you need more than 2 subnetworks, I want you to take your thumb and leave it in the air and bring up another finger and double the value. So instead of saying 2, in fact, I'll draw a hand here. There's our hand. So on your thumb you have a 2, and then you bring up another finger and say 4. And is that enough? No, it's not enough. And so you bring up another finger and say 8. And so you put those 2 fingers down that you don't need. You look at your 3 fingers, and that's how many bits. So your fingers are bits. And it's just a quantity game. We're going to do a couple exercises with this to make sure you are comfortable. It's a quantity game. So if you need 8 subnets, it's going to require 3 bits. And the way we got there is you always start with your thumb. There's a number 2 on your thumb, and your digits represent bits. And the number you say with your mouth represents how many subnets you could create with that many bits. So let's say we needed to create 14 subnets. Let's do it together. You need to create 14 subnets. So you stick up your thumb for quantity. That's all we're after. How many bits does it take? You stick up your thumb and say 2, not enough. Another finger, 4, not enough. Another finger, 8, not enough. Another finger, 16. You say 16, stop, wait, 16's enough? Okay, so look at your fingers. You got 4 digits up, your thumb and 3 fingers. So you've got 4 digits up. That means if you take 4 bits from the actual what was host addresses, you can go ahead and create 16 possible subnets. So it's just a math question at this point. So let's take our original scenario, remove that, and our original scenario is we just need 8 subnets. So my question for you is this: how many bits would we need to take above and beyond the 16 that are currently in the network mask? How many additional bits would we need to create 8 subnets? And the answer is always, stick up your thumb, look at it, imagine there's a 2 on it, and you say that's not enough. Then you bring up another digit, 4, and another digit. So if you're like me and you're saying, Keith, we need 3 more bits to get our 8 subnets, I would 100% agree with that. And then we could go ahead and simply change the mask. Wait, Keith, change the mask? Yeah, change the mask. So 100.1.0.0/19. 16 bits, now 19 bits. Ta-da! That's how you do custom subnetting. Now, well, how do you actually roll that out? Well, that part is also quite simple if we use this technique over here. So if you've done the exercises I've asked you to do so far, you've done the binary and you've written out the keys, I'm going to ask you to take one more leap of faith with me. I'm going to have you write out the mask values in decimal. So this represents 8 bits, the 1, 2, 4, 8, 16, 32, 64. The mask value, if this bit was on right here, would be 128. So if the mask was a 1 and 7 zeros after it, it would be 128 plus 7 zeros would be 128. If we had the first 2 bits on in a mask, it would be 128 plus how much more? Plus 64. So go ahead and take 128 plus 64, and that's 192. If we had the first 3 bits on in a mask and the rest were off, it would be 224, which is 192 plus 32 more. That's why I had you do the binary with me originally, because you're going to use it all over the place. And then if we had the first 4 bits on in the mask, it'd be 240. Why is that? It'd be 224 plus 16 more, plus 8 more. If we had another bit on in the mask, and we'd have 252, 254, and 255. This is another magic key that I would write out. And it's easy to do. I mean, once you've done your binary weight values, and then you simply add the mask values, then this is actually going to give you everything you need to put in IP addresses. So Keith, how do I use this? Well, here's how you'd use it. This represents, so if our IP address is 100.1, that's the network address, and we're now working into the 3rd octet, I want you to pretend that this number here is the 3rd octet. You're going to count over 1, 2, 3, and you're going to draw the line. Just like that. And that represents where the mask is. So the mask will be 3 bits on in the high order position, the rest will be off. But what we've done is, see this number right here? That's your new mask. So if you have to put in a computer, the new mask will be 255, that 255 dot, and for that 3rd octet, we're here right now, we'd put in a 224, and 224 means that we're taking 3 bits above and beyond the default of the 16, or above and beyond the current what we had of 16. So that's half the battle. The last step is, well, what are my new networks going to be? Well, the first network is going to be, and I'm going to put this right here. Actually, this is our first network. The first network looks like the actual previous network, except a different mask. And they call this subnet 0. They call it subnet 0 because none of the bits, none of these 3 bits from the actual network address are on. They're all zeros. So the first network, the first subnet, looks like the original subnet. The only difference is the mask is larger. For the next subnet, you're going to take your block size, which is what this is right here. These numbers I've had you write out several times now are the block sizes as well for your networks. So you're going to take this network, this is the 3rd octet, and you're going to say, okay, the next subnet is going to be 100.1 dot, and for the 3rd octet, you're going to add the block size number, which is 32. For the next subnet after that, you're going to do 1 dot and add it again, add 32. For the next one, you're going to add the block size again, 100.1.96, adding 32, adding 32. And these are your new networks. So guess how many networks we could create out of this? The answer is 8. We did that earlier. So this is just, it's a little bit of a shortcut method. Going to binary back and forth for every single one is a nightmare. And it's not practical, it's not realistic. So by using these values, the mask values, and the block size, we can calculate each of the subnets. I don't expect, honestly, that you'll have to configure subnetting for your Network Plus. In fact, I would bet big money that it's not going to be present for you at this detail. But I can tell you that as you take your skills, my friend, that you're learning here with me, and you apply them to Cisco Certified Network Associate and to Juno certification and to HP certification and Brocade and Palo Alto and all the rest, that those skills will be required. So we're building a foundation and an introduction for those things yet to come. So now that we've done our heavy lifting, let's have some fun and take a look at a few other items that are in this section of the objectives in CompTIA's Network Plus. And the first thing I'd like to do is chat with you about broadcast addresses and what they do and how they operate. So let me bring over a router. In fact, this is our good old router 2. Let's go to router 1. And router 1 is this guy right here that we're dealing with. He's connected to a couple of networks. If we put those in, they would look like this. We'd have the 10.1.0.0 network /24, and over this direction is 10.12.0.0 /24. So that's the two networks he's directly connected to. And one of the things a router, as we'll learn, does is it forwards packets. It looks at IP addresses and makes forwarding decisions based on what it knows. So this router, which is router 1, because it's directly connected to the 10.1 network and the 10.12 network, it knows how to go ahead and get to either of those locations. But what about a broadcast? What does a broadcast look like? I'm going to set up a capture in the background so we can go ahead and capture the traffic as we do some tests, and we'll take a look at the results of that. And I'm going to capture the traffic on this network segment right here. So I'm going to put my wire capture right there, so it's going to look at all the packets, no matter what they are, over the next several minutes as we discuss. So I'll set that capture up, and it is capturing as we speak between R1 and R2. And let's go ahead and send a broadcast packet. Now, what exactly is a broadcast? Well, let me demonstrate one, and then we'll talk about it. If I said ping to 10.12.0.255, you now know what that 255 represents. The 255s is all ones in that last octet. And because this is the network 10.12.0.0/24, this basically says I want to send a broadcast, meaning I want to send an all points bulletin to everybody on that network. See, one of the rules is when we assign host addresses is that you can't give any individual host, like this router or this router, you can't give them an IP address with all zeros. I'll do 8 zeros there, 1, 2, 3, 4, 5, 6, 7, 8 for their host address. And you can't give a device all ones. So let's just assume 1, 2, 3, 4, 5, 6, 7, 8. There's too many. Don't get carried away, Keith. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Okay, so if we're on a /24 network and the last octet was host addressing, this would be an invalid address for a host, and this would be an invalid address for a host. Because when we describe this network, 10.12.0 is 10.12.0.0/24, that all zeros represents the network itself. And let me bring that up just a little bit. And the all ones represent something called a broadcast address. So if somebody sees a packet destined for 255, it basically means I need to forward this to everybody. So it gets encapsulated on the wire as a frame. So this is layer 3, but on the wires we put the destination MAC address in. It's going to be converted to all ones. So the MAC address at layer 2, the destination MAC, is going to be 48 bits of all ones. We'll take a look at MAC addresses as well. So when that gets spit out onto the network, every device, when they see the destination MAC address of all ones, they think, oh, it might be for me. And as a result, every device who sees the layer 2 destination address of all ones is going to de-encapsulate and take a look and see what's at layer 3. And if what's at layer 3 is for them, they'll go ahead and respond. So having said that, we're going to do this ping right here. And what I'm expecting is, because we only have one other device, we have router 2 right here who could respond. I'm expecting a response just from router 2. I'm going to say repeat the ping just one time. So we sent out one ping and we got one reply. Fantastic. But it went out to the broadcast address. So if we had 5 or 10 or 15 devices on that network, they all would have gotten that and they all could go ahead and respond. And that's a broadcast. Now, a unicast is what normal traffic looks like when one device is talking to another. So if I did unicast at layer 3, it would look like 10.12.0.2, which happens to be the IP address of this router right here, and it would send out a unicast ping request for verifying connectivity and would receive a unicast reply as well. So broadcast is when we're sending it to everybody on a given network, and a unicast is when we're giving it to a specific person. And one other item is called a multicast, and it's really interesting. What if this device right here on the network wants to play a network game, and it wants to play this network game with just, let's say we have 5 or 6 other devices, and it wants to play the game with, this is PC1, PC2, this is a printer, this is PC3, and this is PC4, and PC1 wants to play this game, but it only wants to play it with device 3 and 4, and they all need to see the traffic. A multicast is a packet that's sent out on the network that's sent to a group, a certain number. In fact, they call them multicast group addresses. So any frames sent out by this PC would be processed by PC3 and PC4, and any frames sent out by PC3, if these devices were all part of the same multicast group, they would only be processed and de-encapsulated at layer 2 and higher if those devices had joined that multicast group. So broadcast means send it to everybody, unicast means send it to one, and multicast says send it to a group. In this case, we have a group of 3 devices. Now, I've been capturing this the whole time. Let's go and take a look at a protocol analysis of exactly what we sent, and we'll just confirm our understanding of unicast, broadcast, and if we're lucky, we'll even catch some multicast traffic as well. So let's take a look at our results of the packet analyzer that I set up between router 1 and router 2. So I've got a lot of traffic here that's gone through, and we're going to start off by taking a look at a multicast. Now, we didn't generate any multicast traffic, but I've got a routing protocol running between router 1 over here and router 2. And a routing protocol, as we'll learn in a subsequent module or nugget, a routing protocol is a way that 2 routers can share information. For example, router 1 can say, hey, here's what I know about. And router 2 can say, thanks for the information. Here's what I know about. And they can talk to each other. And most routing protocols use a multicast address as they send the advertisements. That way, if there's 4 or 5 routers on the same network, they don't have to send all their information to every other device. With unicast, they can simply send it to the group of routers who have joined that multicast group. So take a look at this address here, 224.0.0.5. That's the destination IP address. And remember our ranges? A class A address was 1 through 126. The class B was 128 through 191. And the class C was 192 through 223. And the class D address, which is our multicast range, starts at 224. So that's an example of a multicast right here. Any other OSPF devices, or devices speaking a routing protocol named OSPF for Open Shortest Path First, they would hear that message and hopefully participate in OSPF if they were supposed to. So that's our multicast. If we scroll down, okay, here's our ping request. So we sent out our ping request to 10.12.0.1, and we actually put in 10.12.0.255. That's what we did at the router. But once it hit the wire, when it got encapsulated, our router actually put in 255, 255, 255, 255, which at layer 3 is an all points bulletin. Everybody who's anybody, this is for you at layer 3. If we take a look at the layer 2 information though, so here's the layer 3 information, where, let me bring this up just a little bit. So here's the layer 3 with the destination address of 255. Get my pen out here. So there's our destination address of this, which is an all points bulletin. It was sourced from us but sent out to the all points bulletin. Let's take a look at the layer 2 information. At layer 2, as it got encapsulated to something interesting. Check this out. The destination address is all Fs. And it says destination broadcast. How does that work again? Well, let's remember how physical addresses operate. A physical address, a layer 2 address, in this case on Ethernet, the MAC address from our previous nugget together is 12 digits long. But look at these digits. We've got CA0013500001, D as in David. So that's our 12 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, do these characters look familiar? I recognize the 0 through 9 and so forth. But what about C and A and D? You know what these are? These are hexadecimal characters. And so with hex, we have that whole conversion of 1 through 9 is the same as decimal. But once you hit 10 in hexadecimal, it's A. 11 is B. We'll jot down here. So we have 10, 11, 12, 13, 14, and 15 is A, B, C, D, E, and F. So each of these characters that you see in a MAC address is really representing one hexadecimal character, and a hexadecimal character is really representing 4 bits. So we have 12 characters that are here, and so 12 times 4 is a grand total of 48 bits. So our MAC addresses, our layer 2 addresses on our Ethernet network, are 48 bits in length. The first half of the MAC address always is the OUI, as we discussed in our previous nugget together. So that's the organizationally unique identifier assigned to Intel or whoever owns that first 6 digits. And then as they make network cards, they make sure the last 6 digits are unique. So they have 24 bits to play with, and that's a lot. That's 2 to the power of 24 different possible combinations, which is millions. So one vendor with one OUI could create millions of unique MAC addresses based on the 24 bits they have to play with for the last portion. And that's the layer 2 address. So we take a look at the destination. The destination is FF, 12 Fs. Now what does F equal? Well, F in binary is 1111. Try to stay on the table here. So what that equals is 48 ones. So as the network sees this, and as the switch sees it, the switch is going to forward that to everybody because it never memorized anybody who lives at 1111. Everybody who sees it is going to de-encapsulate it at layer 2 because it's interesting to them. Virtually every device that's running IPv4 is tuned in to saying, hey, if I see a destination frame of FFFF or 1111 in binary, I'm going to de-encapsulate it and keep on reading. So every device on our network saw this on that network segment. They all opened it up. They looked at the higher layer information. They saw it was a protocol called ICMP, and effectively it's a ping request. And then we had the response. So that's our example of a broadcast ping right here, a broadcast packet with this guy right here. And let's take a look at a unicast as well. Broadcast goes to everybody. Unicast goes to just one. And here's an example with our pings at the end. And I thought we did 5. Maybe I thought we had 5 pings. We could go back and look at that as well. But I'm okay. So here we have the ping source from this source MAC address, source IP address, going to this IP address. And if we look at the details for this ping, which I will highlight right here so that they show up, you'll notice that the source MAC address is from a specific MAC address, and the destination is a different MAC address. And I just want to make sure they're different. So this one is, the destination is CA01 for the first 4 characters, and the source is CA00. So 2 different vendors in this case. Or in my virtual world, 2 different MAC addresses. So coming from me, from my router, going to the IP address, or to the MAC address of router number 2. So I want to have a little checklist of things I want to make sure we covered in this catch-all. We covered broadcasts and what they are. So it's something destined to everybody on the network. Unicast is destined to one, and multicast is destined to a group. We've identified that a MAC address is 48 bits in length. We're leveraging our knowledge of the hexadecimal we had from earlier in this nugget. And, one other thing. Yeah, one other thing I want to cover is that when we're working with IP addresses, sometimes you'll hear the concept of classful and classless. And all that means is that if you're dealing with a classful network, you're paying attention to the default masks for class A, B, and C addresses. Class A is a /8 with the 10 or the 1 through 126, and the class B 128 through 191, and a class C 192 through 223, and the default masks are associated with them, the /8, the /16, and the /24. So if you're working on a classful network, it means that, and there's not too many out there anymore, but classful means you're paying attention and caring about classful defaults that are in place. Any ideas what classless means? Classless means I could care less about what class of address it is. I'm dealing strictly with the IP address, whatever mask I want to assign it with custom subnetting, for example, and I'm not paying attention to the classful defaults that were put in place many, many years ago. And one last thing I'd like to discuss is something called APIPA. A-P-I-P-A. Now, what does that stand for? That stands for the Automatic Private IP Addressing. Now, what does it mean? Well, let's say a computer comes up and it would like to participate on the network, but it doesn't know what IP address to use. Well, if you have 2 or 3 or 4 or 5 devices and they all come up and there's no information on the network, we'll talk about some options we have. But let's say there's nobody handing out IP addresses. They don't know what to do. They can all come up and they can use automatic private IP addressing. And how you know that is the first 2 octets is 169.254, and then they're going to have something in the last octet or 2 for their network. And that's the automatic private IP addressing space. Normally in a production network, if you look at your computer and it says 169.254 for the first 2 octets, something has terribly gone wrong, and you're not going to be able to get too far. So the automatic private IP addressing isn't used in production networks. It isn't used in home networks unless by accident. And so this is a heads up on what that is. So these first 2 octets mean that your computer couldn't find a server who was handing out IP addresses, doesn't know what to do, wasn't statically configured for an IP address, and is doing the best it can to try to communicate with somebody else using automatic private IP addressing. So what have we covered in this nugget? Well, we went above and beyond the call of duty, and we have taken a look at not only what an IP address is used for, which is logically identifying where a device is on the network based on its street and house number, but we also looked under the hood at how it works with the binary that's involved, what the mask does for a living, and also how to create custom subnetworks, or at least how the process is done, which is taking the mask that's given to us and stealing, using the bits above and beyond the mask we're given to create additional subnetworks using the block size to calculate what those new subnets are. We also looked at the concept of a broadcast address, where we're sending it out to multiple people, and there's broadcast address for layer 3. As we take a look, like the 10.1.0.255 is a broadcast address for that network. And we also took a look at layer 2 broadcast address, which is a bunch of ones, 48 of them to be exact, for the destination layer 2 MAC address in a broadcast. A unicast is just going from one device to one other device. And we're with unicast, which is how